In this presentation, we'll look at using the transient response specifications we studied in our last presentation in feedback control systems. Let's consider a feedback control system with a plant P under feedback control of a controller C. So here is our feedback loop. We have a desired signal, YD, being compared to the actual output, Y. That generates an error signal, which goes into our controller, C. The output of the controller is then used as an input to the plant to cause the plant's output, Y, to follow Y sub D. In many feedback control problems, Y sub D consists of a series of step signals, and so we're interested in knowing how this system responds to a step input. How well does Y follow Y sub D in this case? To determine how well Y follows Y sub D, we need to find the closed loop transfer function. And the closed loop transfer function for this system will be C of S times P of S divided by 1 plus C of S times P of S. And we'll denote the closed loop transfer function as G sub CL. We know that if the closed loop transfer function is a second order system or behaves like a second order system, then we can use what we learned in our last presentation to analyze its transient response behavior. We know in this case that the transient response of the closed loop system will depend upon where the closed loop poles are in the complex plane. That is, we can determine how well Y follows Y sub D during the response to a change in Y sub D that is a step input by using the specifications that we just studied, including percent overshoot, rise time, and settling time. Since feedback control can be used to move the poles in the complex plane, feedback control can allow us to tune these metrics of performance. To illustrate these ideas, we'll look at an example problem. Our example problem is an anti-aircraft gun, and we'll look at both the modeling aspects and the control aspects of this problem. The input for this problem is the motor torque applied to the turret of the gun, and the output is the angle of the turret. The motor torque is not applied directly to the turret. It's applied to the motor shaft, and the motor shaft transfers this torque to the turret through gearing. There's significant sliding and rolling friction in the turret bearings, and we have to consider that in our model. So here is a simple model of our turret system. Motor torque T sub I is applied to the motor shaft. This is then connected via the gearing to the turret. Damping acts upon the turret. The motion of the turret is given by the angle. This is the output and is labeled Y. We can make free body diagrams of both the motor shaft and of the turret. The motor torque acts upon the motor shaft, and in response, the motor shaft rotates. This is angle theta 1. There's a force from the gearing that acts upon this shaft, and this is labeled F. For the turret, an equal and opposite force acts upon it. The turret's rotation is given by angle theta 2, and we've chosen the positive direction for this to be clockwise. There's also a damping torque acting upon the motor torque, and this is labeled T sub D. We'll denote the radius of the motor shaft at the gearing as R1. and the inertia of the motor shaft is labeled I1. In a similar fashion, the radius of the turret at the gearing is labeled R2, and the inertia of the turret is labeled I2. For the gearing, we have the following no-slip kinematic condition. R1 times theta 1 equals R2 times theta 2. And from this we can find that theta 1 is R2 over R1 times theta 2. R2 over R1 is referred to as the gearing ratio and is given the symbol K. From the free body diagrams, we can write the following equations of motion. For the motor shaft, we have I1 times theta 1 double dot equals T sub I minus R1 times F. And for the turret, we have I2 times theta 2 double dot equals R2 times F plus T sub D. The relation for the damping torque is T sub D equals minus C times theta 2 dot. We can solve equation number 1 for the gear force F, and we find F equals 1 over R1 times the quantity T sub I minus I1 times theta 1 double dot. We'll substitute this equation into equation number 2 to eliminate the force F. Then we'll perform some algebra and also rely upon the kinematic condition theta 1 equals K times theta 2. That gives us the relation that theta 1 double dot equals K times theta 2 double dot. This allows us to remove theta 1 from the equations of motion. Performing a bit of algebra with these equations, collecting the terms, we find the following. The equation of motion can be written as I2 plus K squared I1 times theta 2 double dot plus C times theta 2 dot equals K times T sub I. We'll note that the quantity I2 plus K squared I1 is the effective inertia of the system. We can Laplace transform this differential equation and find the transfer function between the input torque T sub I and the output theta 2. We find this transfer function to be K divided by I sub E S squared plus CS, where I sub E is the effective inertia, I2 plus K squared I1. We'll now divide both the top and bottom of this transfer function by I sub E. That will give us in the numerator K over I sub E, and the denominator, after we factor, S times the quantity S plus C over I sub E. We'll suppose that K over I sub E is 1 and C over I sub E is 8. And we'll now write the transfer function in this case. It will be 1 over S times S plus 8. This transfer function that we found is the plant. It's the mechanical system that we wish to control. The input is the motor torque, and this would be the output of the controller. And the output of this transfer function is the variable that we wish to control, the turret angle. Since we've labeled the output we wish to control y, we'll give the following relation. Y of s equals 1 over s times s plus 8 times t sub I, and 1 over s plus 8 is our plant transfer function, P of s. So now that we have our mechanical model, we'll turn to feedback control. We have the plant P of s. The controller we'll use is a proportional controller. The controller in this example is a gain, K sub c. That means the output torque, T sub I, is K sub c times the error signal, E. The controller exerts a torque that is proportional to the error. The error signal is Y minus Y sub d. That is, the error signal is the difference between the actual output, Y, and the desired output, Y sub d. Our goal in this example problem is to pick K sub c, the controller gain, so the output Y tracks the input, Y sub d, well when Y sub d is a step input. Let's now find the closed-loop transfer function. This is the transfer function between Y sub d and the output Y, and it's given by K sub c times P of s divided by 1 plus K sub c times P of s. This transfer function is easy to find. We'll simply substitute P of s equals 1 over s times s plus 8 into the form we had on the previous page. And we'll find the closed-loop transfer function as GCL of s equals Kc divided by s squared plus 8s plus Kc. Now that we've found our closed-loop transfer function for our example problem, our next step is to tie this closed-loop transfer function to the transient performance specifications of interest. We'll do this through the closed-loop pole locations. The closed-loop pole locations determine the transient response and are functions of the controller gain Kc. All this will be examined in our next lecture.